All right, everybody, it's time to put Newton's laws to the test. We're going to apply them in these problems. These are the adventures of Mr. Stick and his daughter, Ninita. So if you will please pause the video and try to work these out, and then we'll work them out together. All right, let's see how Mr. Stick is doing here. Mr. Stick, mass m, slides along across a floor with a coefficient of friction of mu with an initial velocity of v. Sketch the velocity and position time graphs with positive to the right. Ooh, positive to the right. So we better pay attention to that right there. So I'm going to mark that up here. Positives to the right. That means we have a negative velocity. We also need to write or always draw our free body diagram. So here we are, we have an mg down, we've got a normal force up, and Mr. Stick is sliding to the left, so friction would be to the right. Force, friction, kinetic. And so therefore these two are equal because we're accelerating to the right. So our acceleration is this way to the right. Now, in our free body diagram, if you ever have to draw one on the test, only put the forces on there. Do not put accelerations, do not put velocities, because they're not forces and you'll lose points. So, what we have here is a constant acceleration, a constant positive acceleration. So, let's see, A. So, here's our X, V, and A graphs. So we have a positive constant acceleration, which means this has to be linear. But our original velocity is negative. So we start off down here at negative v, and then we end at some time with Mr. Sticks at rest. So our final velocity is 0. And then, well, they don't tell us where we begin. So usually in class, we just call the original spot x naught as 0. So let's just say we start at 0, at time 0. But this is a positive acceleration. See, we have a positive slope here. So our xt graph has to be a parabola pointing upward. But he's moving in the negative direction. So it's got to be an upward parabola with an initial negative velocity. So the original slope is negative. And then it's going to curve like this, so that we end up with a slope of 0 at the end, and this time here should be the same time here. So I'm going to call that time s for stop, time s. All right? And that's what they would look like. So be careful of the coordinate system that's given, because that will mess you up otherwise. All right, question B says sketch V and T graphs, or V and X graphs, if mu is doubled. All right, so I'm going to need to get a little bit more information here. So let's go ahead and use forces to figure out what that's going to do to our acceleration. So in the x direction, the sum of the forces equals ma, positives to the right. We have a friction force kinetic to the right, ma, that's mu force normal equals ma, and our normal force in this case equals mg. So that's mu mg equals ma. Actually, these should be capital M's because that's what was given up here. And the m cancels. So the acceleration is going to be mu g. So look what happens. We have the acceleration is proportional to, the coefficient of friction. So if I were to double this, this would be doubled. Okay? So let's do that on this same graph. So I'm going to double my acceleration. So now that's 2a compared to a. So that means I still start with the same velocity, which means that I'm going to have twice the slope. So that means I'm going to end at time stop divided by 2, and that will be twice the slope, 2a. Now I still start with the same velocity over here. It's still a parabola pointing upward. But this time I'm going to have to stop sooner at time s divided by 2. And so it's going to be a parabola. It's going to look something like this. We'll stop at a shorter distance, which makes sense. We won't go quite as far. Deriving expression for the time it takes Mr. Stick to come to rest. All right, so part C. So x naught x, v naught v, a, and t. Let's put all that stuff together. We're starting at 0. We do not know how far he goes. We know the initial velocity is negative v. The final velocity is 0. And then our acceleration we calculated to be mu g positive. And we're looking for time. So, hey, we can just use v equals v naught plus at. And our final velocity is 0 minus v plus mu gt. So the time to stop would be v divided by mu g. And that's it. All right. Now it says Mr. Stick wants to have more fun, so he tries two things: running twice as fast but keeping everything else the same, or doubling his mass and keeping everything else the same. Which one will cause him to slide for a longer period of time? Well, we can tell from right here, in part D here, that time is proportional to the velocity. So if we double the velocity, that will double our time. So that looks good. We can also tell from this that the time is in no way related to the mass. So if we double the mass, this won't change. It stays the same. So our best bet is to double the velocity. All right, Mr. Stick goes skiing. He starts at rest. Assume a frictionless snow of science. Calculate Mr. Stick's acceleration. All right, so let's draw a free body diagram up here, and we have a gravitational force straight down. We have a normal force. Remember that the normal force is always perpendicular to the surface of contact, and there's no friction, so that's it. So since we're accelerating down this way, then I'm going to tilt my coordinate system so I have one parallel and perpendicular to the acceleration. And so that means I need to break up my mg weight into components, parallel and perpendicular. This is the parallel part. This is theta. There's our theta, and this is our theta here. So this will be mg sine theta, and this one on this side will be mg cosine theta. And since we're not accelerating perpendicular, then this one, the normal force, and mg cosine theta must be the same. So we just want to find his acceleration, and he's starting at rest, so that means velocity is 0 and the friction is 0. So for part A, the sum of the forces equals ma. Our only force down the incline is mg sine theta, and that equals ma. So the m cancels, so our acceleration is g sine theta, and that wasn't too bad. All right, part B. What is his velocity after traveling a distance L down the slope? So I'm going to need some kinematics for this. So x naught x, v naught v, a, and t. Let's get organized. We didn't say where we started, so let's assume it to be 0. We're going a distance L. The initial velocity was 0 because we started at rest. Our final velocity is what we're looking for. And our acceleration is g sine theta, and we do not know the time. So that looks like we're going to have to use v squared equals v naught squared plus 2ax minus x naught. And let's take out all of our zeros. Our initial velocity is 0. Our initial position is 0. So v squared equals 2ax, or v squared equals 2g sine theta times L, and I'm just going to square root it right here, and there is our answer. Put it in square root. All right, after traveling a distance L, Mr. Stick hits an unfortunate patch of mud and comes to rest in a distance of 2L. So he goes a distance L, and then he's going to end up stopping. I'll just put it down here, 2L. All right, so sketch the velocity time graph and the acceleration time graph of his tragic journey. And here is, we're going to have a certain amount of time. It's going to be less of the time that he was accelerating forward. So he's going to be accelerating forward. So that means we're going to have a positive slope up like this to this point. And then he's going to slow down, and he travels twice as far, So the acceleration must be less, but it's negative, in the negative direction. So I'm going to go like this. I'm going to make my acceleration less, and we're going to go out a farther amount of time because it's going to take them longer to stop than it took them to accelerate. And so that means our slope over here will be something like this, going out a little farther. And so we have a negative acceleration here and a greater positive acceleration on this side. All right, if we start at rest, we should have a steep slope here. For the first part, that's positive acceleration. And then a lesser sloped or changing slope, parabola downward. So it's going to travel slower this way. So it should look something like that. And that's the inflection point right here. All right, part D. Derive an expression for the coefficient of friction of the mud. Oh, that sounds pretty hard. So let's see, what adds to this? So let me just add in what happens with our mud. So now we have a force of friction backwards that's kinetic. All right, so that means our equation up here has changed. Instead of it just being mg sine theta, now we have subtraction of our force friction kinetic equals ma. And this equals mg sine theta, and our friction is mu normal force. But our normal force we already know has to be mg cosine theta. All right? So this is going to be mu mg cosine theta equals ma. Cancel out our m's, and we have g sine theta minus mu g cosine theta equals a. And we're looking for coefficient of friction. So g we know, theta was given in our picture. We don't know the acceleration though for this second part of the journey where the acceleration is this way. So I've got to find that out. So how am I going to do that? Well, we can use kinematics. So x naught x, v naught v, a and t. Let's get organized. I'm going to call this spot here. So this distance was 2L from here to here. And this was when he traveled L. I'm going to call this 0. And then he traveled 2L. So I'm just going to make it easy on myself. He traveled from 0 to 2L. That's the distance he traveled. His initial velocity is right here when he hits the mud is this. Oh, that's ugly. So that's 2g sine theta L square root. Uh-oh. Final velocity is 0. We don't know the time. We're looking for acceleration. So, well, that's the same equation we used before. V squared equals V naught squared plus 2a x minus x naught. Get rid of our zeros. That's 0 and that's 0. So we have 0 equals, hey, this gets squared. So the square root goes away. That's nice. So we got 2g sine theta L plus 2a, and this is 2L is how far he travels. So if a 2L here and a 2L over here cancel out, and so I'm left with an acceleration that's negative g sine theta over 2. Hey, that makes sense. Look, he traveled twice as far. He now has half the acceleration he had before in the opposite direction in order to bring him to rest in twice the distance. Okay, well that makes sense. All right, now I'm going to take this, I'm going to plug it in here, and I'm going to get g sine theta minus mu g cosine theta equals negative g sine theta over 2. And a little bit of mathematics occurs. Our g goes away. All right, let's rewrite our equation because this is starting to mess me up a little bit. So here we go. I'm going to get sine theta minus mu cosine theta equals sine theta over 2, and that's negative. I'm going to get rid of my negatives by moving the negatives to the other side. So this one's going to come over here, and the mu is going to go over there. So I get sine theta plus sine theta over 2 equals mu cosine theta. These two add up to be 3/2 sine theta equals mu cosine theta. And then I divide and I end up with mu equals 3/2 tangent of theta. And that was way too long of a problem. So let's take a look at our last one. Hopefully it's easier. It says, sketch the energy versus distance traveled graph for Mr. Stick's misadventure. All right, I got some space over here, so let's do this. Here's energy versus location. So here's where he begins. Here is L, and here is another 2L beyond that. So that would be 3L total. Okay, so this was a little messed up here. I should have said that this is 2L between and this is 3L, so as not to confuse everybody and myself. All right, so at the beginning, we start with gravitational potential energy at the start, and then he slides down the slope, and as he does, he's going downward. So if he slides down the length of the slope, his potential energy will decrease at a linear rate because gravitational potential energy is mg delta y, and as he goes down the slope, that's going to be a change in y. So this should be linear all the way to the bottom, and I'm going to call the bottom 0. So he ends up down here with 0 gravitational potential energy. All right. Now, kinetic energy is 1/2 mv squared, and I don't know how the velocity changes with location. I mean, I know what the velocity is here. It's something, and I know the velocity here is 0. So I know at the end, the kinetic energy has to be 0. And I know we started with kinetic energy of 0. So what's it like in between? Well, as he's sliding down with no friction from here to here, there should be no energy loss. So from here to here, the total energy should be constant all the way to right here. So this is total. So that means if the potential is decreasing, the kinetic should be increasing, and so that should go up towards here, and this value here and this value here should be the same. And so when I add this to this, they should end up equaling the total. All right, so how does the total energy go from there? Well, remember that work equals the change in energy, and work equals FD cosine theta equals the change in energy. And our force will not be changing because our friction is constant as he slides down. And so that means the change in energy is proportional to the distance he travels, so that should be linear. So that means that the total energy should go here linearly as well, which means that our kinetic energy should go from here to here. We end up with no energy at the end. So the orange line right here is our kinetic energy. Our pencil line is gravitational potential, and the red one is the total, TE, total energy. That last problem was no fun. Let's see if this one's any better. Mr. Stick takes Ninita, who has a mass of m, to the playground for a swing. What force does Mr. Stick have to push to hold Ninita in place as shown? So let's draw our free body diagram over here. So we have a gravity force down. We have a tension force up this way. And we have, I'm going to assume he's pushing to the right. I really don't know. It doesn't say. I'm just going to call it F. All right? So she's staying in place. So all I have to do is these two must be equal in the x direction, and this one in the y direction must be equal. So I can just set that up right here. In the x direction, F equals, what would that be? That would be T sine theta. And in the y direction, do that over here, I know that T cosine theta must equal mg. And I'm looking for his force, so let me solve this one for T. That's T equals mg over cosine theta. I'm going to plug that in here, and I get that his force will be mg tangent of theta. All right, that wasn't so bad. That's called a statics problem, where the thing is at rest and not moving. All right, Mr. Stick gets tired, so he attaches a string to hold Ninita up as shown. Which string has the greatest tension? Explain using equations. All right, so here's the thing that most students do is that, let me draw it down here. They will draw the tension forces the same sizes as the string. So here's tension 1 and tension 2. And then here's the gravity force down. Okay, that's fine for your first sketch, but the thing is that when you break these into components, you see that this x component is way too large to the right. So I need to shorten that up by making this tension smaller or making this tension bigger. It's easier for me just to make this one shorter. And so what I end up with, they have to be the exact same length, so they're going to be way down here. So this one is equal to this one. And so as you can see, T2 is much smaller than T1. So T1 is greater than T2. By the way, just as a side note, we do know that T1 in the y direction plus T2 in the y direction, these upward pieces right here and here, have to equal mg downward in order for this to be static. All right, let's look at our last problem. The string breaks. Ninita is traveling at a speed of s at the bottom of the swing. What will the tension be in the swing at this point? All right, so I put this in here again because it's an easy one to mess up, because what we do all the time is we say, oh, it's at the bottom, so there's a tension force up, and then there will be a gravity force down, and we say, oh, they're equal. But the thing is she's going through an arc. Since she's going through an arc, she's changing direction. Therefore, she's accelerating towards the center, so the tension must be bigger. The sum of the forces towards the center equals MAC. So that means tension up minus her gravity force down equals mv squared over r. And so the tension would be equal to mg plus m, and her velocity is s squared, and the radius is d. And you can even factor out the m, so it's g plus s squared over d. And there's our answer. All right, last one. So in this one, it says Mr. Sticks wants to go faster. So he attaches Ninita to the massless rope of science and passes it over a massless frictionless pulley of science. Mr. Stick puts the frictionless socks of science on, and he lets her go. So derive an expression for the acceleration of the system. So I need to draw a free body diagram. So I've got her mass down, mng. I have a tension force up, and that tension force has to be smaller than the gravity force down, because it's all going to accelerate this way. So the string up here pulls down T, same tension, from here to here. And then this, since it's the massless frictionless pulley of science, then this will just be T over here. Same. And that will be T over here. Same. And then there's a gravity force on him downward, MSG, and a normal force up, which the normal force up and the gravity force down have to be the same. Now, one last thing, this pulley over here will not stay in place if there's tension this way and this way, unless there's another force. So there has to be a force out this way. And it'll be at a 45-degree angle, actually, since these two are the same. And it's the normal force that cancels out these two, or the force from the axle, if you prefer. All right, so we're trying to find the acceleration of the system. So let's write Ninita's equation. So the sum of the forces equals ma downward. So mng minus tension equals ma. Now let's do Mr. Stick, and that is the sum of the forces equals ma, but now in that direction. So the tension, that's it. equals msg. Now I can plug that in over here and I get her mass, her weight, minus his weight equals ma. Which a is this one? I didn't put down what the subscript is, so let's pay attention here. This was for the girl, so this is n. Hey, I've made a terrible mistake here. Does anybody see it? It's right here. I put G down. It should be A. Well, I make mistakes just like everybody else, so you always have to keep an eye on me. It's time for me to go to bed. All right, so that's A. So, because T equals MA for Mr. Stick. All right, so I need to move this to the other side. So I get MNG equals MS plus MN times A and divide. So I get the acceleration to be MNG over MS plus MN. Hey, and if you take a close look at this, this is the force that's making it all go right here. Her weight. And this is the mass of the system. So this is essentially F equals ma for the system. The force that's making it go divided by the mass of the system. All right, excellent. That'll help us out just a little bit. So part B, keeping all the other variables the same, explain how each change will affect the acceleration. Will the acceleration double, be cut in half, or stay the same, or something else? So for part B, if we double Mr. Stick's mass. So let's take a look at this. He's right here, Mr. Stick. It's in the denominator. So the acceleration will decrease. Will it be cut in half? Well, if it was only his mass, then yes, it would be cut in half. But it's his mass plus something else. So if we double this, there's something added to it. So it won't completely be cut in half. So it's not acceleration divided by 2, all right? But it will decrease. All right, part C, what if we double her mass? So her mass, double it. Well, that should double this, right? But she also shows up as part of the inertia. So we have a 2 in the numerator and a 2 in the denominator. So the 2 in the numerator will totally double the numerator. The 2 in the denominator has something else added to it, so it won't completely double. So the acceleration will increase, but not double. All right, how about D? If we double both masses. Now, if we double both masses, we get a 2 here, and a 2 here, and a 2 here. This 2 will factor out, and we'll end up with a 2 in the numerator and the denominator, and they'll cancel out. So the acceleration equals the same. It won't change at all. And then E, what if we add friction to Mr. Stick's socks? All right, so if we add friction, then we would add another force friction this way, which would force friction this way, which would decrease the net force. We'd end up with a friction force in here, subtracting off from our net force. So that is going to decrease our accelerations. The acceleration decreases, but we don't have any idea how much because we don't have enough information to go on. So we do know it decreases. How about F? The pulley has mass, but no friction. So what if we just add mass right here? Now, if we add mass to this pulley, then we add inertia to the pulley. And therefore, this tension will have to be larger than this tension in order for it to go. So this one has to be bigger than that one, which means the tension pulling on Mr. Stick will be smaller. So therefore, his acceleration will be less. So the acceleration will decrease. We just don't know how much because we would need more information to know how much mass this pulley has and rotational inertia and all that. And that's going to show up in our next video. We're going to talk about forces and how they produce torques and how that affects the rotation of an object. All right, till then, bye.